We will now look at the Cantor function. So please recall the Cantor set. So we took 0, 1 and then we removed the middle third, and then with the remaining intervals we removed the middle third and so on, and what was left was the Cantor set, and this set was an uncountable set of measure 0 and which was nowhere dense. Okay, so now the Cantor function, like the Cantor sets, provides a lot of interesting examples and counterexamples to illustrate various fine points in the theory of Lebesgue integration. Several constructions are possible, and always the final properties of the function which you get are the same, and they all serve the same purpose. So we will describe one such construction. So before we do that, to make it easier, let me just illustrate a certain basic construction. Let us take an interval AB, and then you have a linear function. So this is f of A and this is f of B. Okay, so f of x is equal to f of A plus fb minus fa by b minus a into x minus a. Okay, for all x in AB. So now we divide this interval into 3 equal parts. Okay, so these are C1 and C2. So Cj is nothing but A plus j times b minus a by 3. J equals 1. The value at C1, f of C1, is equal to, of course, because it's a linear function, we are taking the 1/3 point, that will be 2 times f of A plus f of B divided by 3. Okay. Now we then define the next iterate of this function. So what we do is so again let me draw it again. So this is f of A, f of B, this is A, this is B, and you have C1 and C2. So up to C1 we follow the function, and then from C1 to C2 we go horizontally. Okay, so this is f of C1, and then from here you climb up to get the new function. So this is the new function. So g of x is equal to f of x if x belongs to AC1 and is equal to f of C1, it's a constant, if x belongs to C1, C2, and then you have f of C1 plus fb minus f of C1 by b minus C1 into x minus C1. So this is for x belonging to C2. This is f of C1 because that's the same value, but b minus C2 into x minus C2 for x belong to C2b. So this will be the new function which you have. So you follow the function up to C1, then you do a constant, and then you do this. Okay. So now a simple calculation will show that the slope on C2b will be twice that in AC1. So this slope and this slope will be exactly double the slope of this. That's a very standard, straightforward calculation which you can do from the whatever is given to you. Okay, so now let us consider the interval 0, 1. and we take the function f0x equal to x, and then we apply this procedure. So we have here 0 1, okay. So now we apply this procedure. So we have 1 by 3 here, and you have 2 by 3. So in this part, up to this part, we will keep the same, and then we will go horizontally up to 2 by 3. And from 2 by 3, we will go climb up. Now what we will do is we will leave this constant portion simple. So here we have, you have 1 by 9, and then 2 by 9, and then similarly you have two portions here. So here we will go along this function in this interval, and then we will go as a constant here and then climb up to this function. Similarly here we will go along this function up to this point, up to the 1/3 point, then go horizontally up to this, and then you construct. So this is f1, this is f0, and this is f2. Okay, so once it's a constant, it's always constant. So now f3 will be, you will have to divide this intervals into 3 equal parts, follow the function on the first part, go horizontally in the second part, and climb up to the third part. Okay, so this is the construction which we are going to repeatedly do at different scales. So in this manner we can construct, so in this way we iteratively construct continuous, piecewise linear, non-decreasing functions fn. Okay. If fn is constant on any subinterval, then for all m greater or equal to n, fm equals fn equals same constant on that subinterval. Once it's a constant, you don't meddle with it. You always apply this construction only in the non-constant parts, that you divide by 3 and go on. Okay, so the union, notice that the union of subintervals where fn is constant is precisely the set xn of middle thirds used in the construction of the Cantor set. So go back, I'm using the same notation here. So the maximum slope, so also fn is less than or equal to fn plus 1 for all n, because when you do this construction you will see that you are following, then you are falling below, and then you are climbing up. So each time the function is less than the previous, fn plus 1 and each fn is monotonic, non-decreasing. Okay, so sequence is decreasing pointwise, but the function is increasing, is an increasing function. Now maximum slope occurs in the last subinterval. Each time we apply the procedure, the slope is doubling, and therefore thus in the last subinterval of length 1 by 3 power n, the slope will be 2 power n, because we started with the slope 1 in the original function, and every time in the last interval it's going to double. We have applied it n times, and therefore we get 2 power n as the slope there. Therefore for all x in 0 1, by the mean value theorem, we have that mod fnx minus fn plus 1x. This need not be a modulus because this is a non-negative quantity. This is less than or equal to the maximum slope which you have in fn plus 1 minus fn plus 1 by 3 power n plus 1, and that's less than or equal to 2 by 3 power n plus 1. Now sigma 2 by 3 power n is convergent because of the geometric series, and therefore this implies that fn is uniformly Cauchy. So if you have sigma an such that an minus an plus 1 is less than Rn, sigma Rn is convergent, this means that an is Cauchy. Sorry, not sigma n. You have a sequence an. Subsequent terms are in a convergent series, then this is Cauchy. This is a easy fact to prove, so you should be able to convince yourself about this. And this is uniform for all x in x we have, and therefore you have uniformly Cauchy. Okay, so you have a uniformly Cauchy sequence on an interval. That means that fn converges to f uniformly on 0 1, and f is a continuous, because it's a uniform limit of continuous function. F is a continuous function and it is also non-decreasing, and this function is called the Cantor function. So first f is fn non-decreasing for every n implies f is non-decreasing. 2, f is constant on each subinterval of C complement, where C equals Cantor set. We saw that once it's a constant, it's constant in Fn all along, and these sets are precisely the middle third sets, and therefore they are the complement of the Cantor set. Okay. And then 3, f of 0 is 0 and f of 1 is 1. So now define psi of y equals y plus f of y, y in 0, 1. Then psi is strictly monotonically increasing, because I've added y here. This is a non-decreasing function. I've added a strictly increasing function. Therefore, this is you have. And you have psi of 0 is 0 and psi of 1 equals 2. Therefore, psi is from 0, 1 on to 0, 2, and this is a bijection. So we have phi from 0, 2 to 0, 1, inverse then phi is also monotonically increasing. Okay, and you have that x equals phi x plus psi of f of for every x in 0, 2, because you have phi is the inverse function. Now if x is bigger than or equal to y, then you have phi x is greater than or equal to phi of y, okay, and x minus y equals phi x minus phi y plus f of phi x minus f of phi y. F is non-decreasing, and therefore this is greater than or equal to 0, and therefore this shows that phi x minus phi y less than or equal to x minus y for all x greater than or equal to y, or in other words, mod phi x minus phi y is less than or equal to mod x minus y, and therefore phi is continuous as well. So now psi is a bijection, implies it maps disjoint sets into disjoint sets onto. So if I contained in C complement is a subinterval, then f restricted to I equals some constant, which is some, let's say, C of I. Therefore psi of x equals x plus Ci on I. So psi just translates each subinterval of C complement. So M1 of psi I equals M1 of I for each I contained in C complement subinterval. And C complement is the disjoint union of all such subintervals and psi maps disjoint sets into disjoint sets, and therefore you have m1 of C complement equals psi of C complement equals m1 of C complement, and that's equal to 1. So this implies that m1 of C itself has to be equal to 2 minus m1 of psi of C, psi of C complement, and that's equal to 1. So in other words, this function psi maps C a set of measure 0 onto psi of C a set of measure 1. So m1 of psi C equal to 1, which is strictly positive. Therefore there exists S contained in psi C, S not Lebesgue measurable. We saw that every positive set contains a non-Lebesgue measurable subset. Okay. So let M equal to psi inverse of C, S, and of course you can call this as phi of S, because phi is nothing but psi inverse. So M is this, and so M is but M is contained in C. Measure of C is 0, the Cantor set. Therefore by completeness of the Lebesgue measure, M is Lebesgue measurable. Claim M is not Borel measurable. So you see, we have if this claim is satisfied, so we had P, and then we had R, and then we had B1, then we had L1, and then we had power set of R. And we saw explicitly there are non-measurable subsets. So this is here. We gave a unsubstantiated but cardinality argument to show that this is also strict. But now we are giving an example of M which is Lebesgue measurable, but it is not Borel measurable. Okay, so if not M Borel measurable, implies S equals phi inverse of M Borel measurable, because phi is continuous and so Borel measurable. But that implies if some set is Borel measurable, it's automatically Lebesgue measurable. S is Lebesgue measurable, but that is not true, because we have S is not Lebesgue measurable, so this is not true. Therefore the claim is substantiated. So we have M is Lebesgue measurable, thus, but not Borel measurable. Finally, let us set capital phi equals chi of M. So this is a Lebesgue measurable function, because M is a Lebesgue measurable set, therefore it's a Lebesgue measurable function. Now you take zeta equals phi composed with phi. So zeta is a composition of a Lebesgue measurable function and a continuous function. Continuous functions are both, so phi Lebesgue measurable, small phi is continuous, implies Borel measurable implies Lebesgue measurable. And you are taking the composition of two Lebesgue measurable functions. So now if you took zeta inverse of the singleton one, this is equal to set of all x in 0, 2. What is zeta? Is capital phi or small phi of x. This is phi of x belongs to M, which is equal to phi inverse of M. And that is S, but this is not Lebesgue measurable. But so zeta is not Lebesgue measurable. Because we did this exercise, we know that if the converse is not true, but this proposition, if a function is measurable, then the inverse of every singleton has to be measurable. And here you have a function which is 1, the inverse of the singleton 1 is not measurable, and therefore the original function cannot be measurable. Therefore, composition of measurable functions need not be measurable. So this Cantor set will have many more applications. So before we close, I want to make some this thing about almost everywhere. Now that we have what do we mean by this? A statement which we will have. So XS measurable space, mu a measure on S. Then we say XS mu is a measure space. We have a measurable space XS, which means you have X and a sigma algebra, and now if you specify the measure also, then you call it a measure space. So we say a property holds almost everywhere if there exists a set E contained in X, mu E equal to 0, such that the property holds on E complement. So when a property holds almost everywhere, we means it's true except possibly on a set of measure 0. So let us give some examples. So a measurable real valued function extended real valued function is finite almost everywhere. So when we say almost everywhere, the short form is AE, is finite almost everywhere if there exists a set E, mu E equal to 0, and fx belongs to R for all x in E complement. Fg measurable functions on a measure space xs mu, we say f equal to g almost everywhere if there exists a E contained in X, mu E equal to 0, and fx equals gx for all x in E complement. Given a sequence of measurable functions fn and a measurable function f defined on x, we say Fn converges to f almost everywhere if there exists a E contained in x, mu E equal to 0, and Fnx converges to fx for every x in E complement. So this gives you an idea of how we use the word almost everywhere. So in this context, we will also make the following definition. Xs mu is a measure space f x to r measurable function. F is essentially bounded if there exists m greater than 0 such that set of all x in x such that mod fx is greater or equal to m has measure 0. So that means except for a set of measure 0, mod fx is less than or equal to m. And then we define norm f infinity to be the infimum of all m such that measure of set of all x in x mod fx greater or equal to m equal to 0. So all such m which occur here, so this is called the essential supremum of f is called the essential supremum. That means except for the set of measure 0, this is the smallest number, smallest lower bound, upper bound. So, okay.